Okay, welcome back, Regents students. The topic for today is sound. So the first thing that I want to talk about is how sound is created. Sound is created by vibrating objects. Right now I'm talking, so my vocal cords in my throat are vibrating, moving forward and backwards. But it could also be a musical instrument, the reed in the musical instrument vibrating, creating sound. Or in a brass instrument, it could be the player's lips vibrating. Or it could be a speaker, like when you put on your headphones or just your computer speaker. In the case of a computer speaker, the speaker is like a cone that's vibrating forward and backwards, and when it lunges forward rapidly, very quickly, it compresses a layer of air because it squeezes that air. And then that squeezed layer of air, when the speaker retreats, it's like a balloon that's been popped because there's no boundary holding that air squeezed in. So it expands rapidly, and as it expands, it squeezes the next layer of air, compressing it. And in the meantime, the speaker continues to oscillate, so makes the next compression and recedes. This layer then pops open like a pop balloon, squeezing the next layer of air, and so on and so forth. So as the speaker is creating compression after compression, the compressions are traveling across at a certain velocity. This makes the sound a longitudinal wave because it's made of compressions where the air is squeezed in and rarefactions where the pressure is low. In other words, the air is kind of stretched out or lower density. And also those vibrations forward and backwards are parallel to the wave motion that makes a longitudinal wave, compared to what we learned yesterday. When you vibrate something like this and then the wave moves this way, we've got a perpendicular vibration compared to the velocity. That's a transverse wave. The other point is that sound is, like all waves, a movement of energy, not of the matter. If I'm talking to someone 50 feet away, opposite end of a hallway, they can hear me. So the vibration of my vocal cords goes into their ear. The breath out of my mouth doesn't go into their ear. Give you an example. If I ate an onion for lunch, so you're standing next to me, you could smell that onion. But if I'm talking at one end of the hallway to another person at the opposite end of the hallway, they're not going to smell that onion. They're going to hear the vibrations, so the air coming out of my mouth just kind of stays here. But those vibrations go a long distance, so the transfer is of energy, of the vibrations, not of the air coming out of my mouth. Okay? Another point, obviously, is that sound, as I just explained, is vibrations passing through atoms. So this is something that the Regents likes to emphasize. Sound, no sound is possible in a vacuum because there are no atoms there. So tomorrow's lesson will be about light, and obviously the sun sends light to the earth, lighting up, giving us the day. So the light we're going to learn tomorrow can travel through the vacuum of space. The sun, we do not hear it when it comes up. It's silent. Does that mean the sun is really silent? No. The sun is made of nuclear reactions. And think of a nuclear bomb going off. That's definitely loud. That sound is at the sun, but it cannot go through space, the vacuum of space, because there's no atoms to vibrate. So we cannot hear the sun's sound, only see its light, which can travel through vacuum. Okay, so sound goes through matter, and it goes at certain speeds. This is the speed of sound in air. I didn't write it, but maybe we should have wrote in air over here. It's 331 meters per second at STP. STP means standard temperature and pressure. In other words, 0 degrees Celsius, which is the temperature at which water freezes, and at 1 atmosphere was basically at the pressure at sea level. So if you're standing next to the ocean on a cold day, then the speed of sound is roughly 331. Like all numbers, you don't have to memorize this number in the Regents curriculum. Here's our reference table front cover where we find a lot of different numbers like 9.8 and so on and so forth. Pretty close. Fourth one down, speed of sound in air at STP is 3.31 times 10 to the 2 meters per second, which is 331 meters per second. So you could just write it as 331 in your calculations. Here's a formula that's not in the curriculum. You don't need to write any of these down if you don't want to. The point of this formula shows that as the temperature in Celsius goes up, so does the speed of sound in air. So at 10 degrees Celsius, for example, we would go 10 times 0.6 or 6 faster than 331 or 337 meters per second. So sound will travel somewhere in this room right now, room temperature, somewhere in the 340s, for meters per second. If you need that number, it would have to be given to you in a problem. So they would have to tell you the speed of sound in a room is 345, and then they go on with the rest of the problem. In water, sound travels surprisingly very fast, 1,402 meters per second. Most people they probably think that sound travels poorly in water. And the reason for that is that when you may have experiences of going underwater and trying to talk to your friend, and all you hear, your friend would hear, is like a jumble of bubbles. That's because the sound is made in your throat with air, and then when that air comes out of your mouth, it comes out as bubbles, distorting the sound. If you had a speaker, though, that was designed to operate underwater, in other words, the speaker material had water all around it and it was vibrating in the water, or you had the sound producing parts of a dolphin or a whale, the sound would travel very fast and very clearly in water. Okay. In steel, it's even faster, almost 6,000 meters per second. The reason why is these substances are not very compressible. That means that, like, take water, if you try to squeeze it in a piston, it would hardly squeeze at all. And so it makes it very springy. So when that speaker lunges forward and compresses, it springs very quickly and compresses the next layer, so the sound goes very fast. All right, so what kinds of calculations might you have to have with velocity? These are a couple formulas. This is the classic formula in the mechanics section. D equals VIT plus 1/2 AT squared. The 1/2 AT squared is not written because the sound doesn't accelerate in air or in other materials. It just goes at a constant velocity. So the calculations here, pretty basic. But I'll give you an example of a couple without actually writing them out. Let's suppose you want to know how long it takes sound to travel across a football field. Football field's 100 meters roughly, so you put in 100 meters here. And let's suppose the problem tells you that we're at STP, so you put 331 here, 100 here. You divide the 331 to the other side, and you get about 0.3 seconds. So that means that it takes that long for the sound to go across the football field. You may have experienced this watching a baseball game. You see the batter hit the ball, and you don't hear the sound yet. That's because light travels, we're going to see tomorrow, extremely fast. So it gets to your eye in an instant. And then the sound sort of lumbers behind and takes 0.3 extra seconds to get to your ear. So you see the ball hit, then you hear it hit. Okay? Another common calculation, this has sometimes some interesting practical applications. Let's suppose you see a lightning strike, so the sky flashes. And then later you hear the roar of thunder. Let's suppose you time with a stopwatch the difference between those two things, those two observations, and you find that from the flash to the time you hear the rumble is 5 seconds. So you plug in 5 seconds here, and a reasonable estimate for the speed of sound on a summer day, let's say, is 340, just, approximate. So 340 times 5 seconds gives you about 1,700 meter distance. What that tells you is that the lightning struck 1,700 meters away from where you are, which is about a mile. 1,600 meters is a mile. So as a rough estimate, for every 5-second delay, that corresponds to the lightning strike being 1 mile away for every 5 seconds. The other calculation is with this formula that we learned yesterday. Basically, speed of the wave, 331, wavelength and frequency. You're given 2 of these and you're asked to solve for the third. So the algebra is pretty straightforward on this topic. Okay, so some other things that I want to mention. Range of human hearing. So you may have heard of a thing called a dog whistle. A dog whistle, you blow this whistle and you don't hear anything. It's silent. But if you have a dog, your dog's ears perk up. Okay, so the dog can hear the whistle, but you can't, because we can't hear above a certain frequency. Human ears can hear somewhere about between 20 hertz and 20,000 hertz. So at the end, within this assignment, I've included a link that you can go on the web and you can put in any frequency you want, and it'll play it over your computer speakers. So go open that link if you're interested at the end. Plug in 100 hertz and let it play the tone. You'll hear like a low bass sound, okay, like a bass guitar kind of tone. And then go up by hundreds. Listen to 200, 300, 400, 500, up to 1,000. And so you get a sense of what these frequencies sound like, okay? And then once you get to 1,000, you could go up by thousands. So from 1,000, go to 2,000, 3,000, 4,000. Keep going up until 20,000. What that means is that let's suppose you're at 10,000. Your computer speaker is going in and out 10,000 times per second. That's an enormously fast vibration, 10,000 times per second. And then those compressions are going into your ear and hitting your eardrum 10,000 times in 1 second. And then that vibration of your eardrum goes through the nerves into your brain, and your brain then perceives that tone that you're hearing. Okay, so that's how the sound waves work, how they're created by the vibration, and then your eardrum gets hit with that same vibrational frequency and you hear the tone. The wavelengths of each. 20 hertz, if you want to find out the wavelength of the lowest bass sound you can hear, use V equals lambda times frequency. I used about 340, plugged in 20 hertz, and I got about 17 meters. 17 meters is about the diagonal length of our classroom at Clarkstown. So that's how far it is away. When the speaker makes one compression and then the next, they're 17 meters apart with the lowest bass sound you could hear. At the highest whine of 20,000 hertz, the speaker is vibrating in and out so rapidly, if you calculate the wavelength, you get 0.017 meters or 1.7 centimeters, about that far apart. So that's how far apart each compression is that goes into your ear, races in and strikes your eardrum and makes it vibrate to make you perceive the sound. So if you're interested, go up, and at some point what you might find with the sound wave generator is that at some point you may not be able to hear the sounds anymore. Let's suppose you get to 14,000 hertz and you can't hear anything. There are a couple possibilities. One is your computer speaker is, not the greatest, so it can't make that sound. So your speaker has failed and it's not making that sound, so you can't hear it. That's one possibility. The other possibility is that you have some hearing damage. The first thing that you lose, a human typically loses with hearing loss, is the high-end sounds. And so that's the first thing that goes. And you might be saying, well, who cares about losing the high end? When do I ever hear those squeaky sounds? You hear them actually all the time. People don't talk at those frequencies. But when they make sounds with their mouth and speech, like an S sound, when I say sound, that S sound, or if I say the, right, and I'm saying that sound with a TH sound, those kinds of sounds are very high frequency. And when you lose the ability to hear those sounds, and so you're talking to someone with hearing loss and you say he, right? So now someone with hearing loss hears not the first part, the H sound. They only hear the E part. So maybe you're talking to your grandparent and they hear E went to the store. And they think, was it was it he or she, or did you say see the store, right? So they don't know what that first sound is. They get confused. So they say what? And then you have to repeat it, right? So then they could try and put it together with the brain and fill in those missing sounds. So that's the problem with hearing loss. When you start losing those high ends, you start to be unable to distinguish different words from each other, and it makes you confused. So loud music, of course, could be causing that. Concerts, you definitely want to be cognizant of that. The last point I want to make is about sound frequency versus sound amplitude. What does it mean when a sound has a higher frequency? Well, we just heard, and you can see it through that wave generator, that sound generator, it's more of a whine, the higher frequency you get. The sound amplitude is the loudness. So this is what this is saying. If the frequency of sound increases, the sound gets more like a squeak, like a small chirping bird versus a hawk. That's a higher frequency. If the amplitude of the sound increases, the sound gets louder. So here's an example. Listen to Ariana Grande on low volume, then play the same song on full volume. Ariana Grande's voice sounds the same. It's not more like a squeak or more like rumbling thunder. It's her voice, the same tone. It's just louder at a bigger amplitude. And that's something that the Regents likes to emphasize also. Amplitude means louder. More amplitude, sound is louder. Okay, so that's the sound lesson. And now, as always, complete the homework. Let me know if you have any questions. And I'll see you in the next video. Light.